If you've been impressed by AI generating human-like text, answering complex questions, or writing code, you've witnessed the power of large language models, LLMs. These are at the forefront of generative AI for text, and they are built almost exclusively on the transformer architecture. Recall our previous discussion on transformers. Their ability to process all words in parallel using self-attention and their scalability made them ideal for training on vast datasets. LLMs take this to an extreme. They are transformer models trained on colossal amounts of text data, billions of words from the internet, books, articles, code, and more. The large and LLM refers to two things: the scale of the data they're trained on and the number of parameters they possess. Models like GPT-3 have billions, even trillions of parameters, allowing them to capture incredibly subtle patterns and relationships in language. What do LLMs actually do? At their core, they are highly sophisticated next word prediction machines. Given a sequence of words, an LLM predicts the most probable next word. By repeatedly predicting the next word, they can generate entire sentences, paragraphs, or even full articles that are coherent, contextually relevant, and grammatically correct. Their strength comes from their deep understanding of language structure, grammar, facts, common sense, and even subtle nuances learned from this massive training data. This emergent capability allows them to perform a wide range of tasks: text generation, writing essays, stories, marketing copy; summarization, condensing long documents; translation, as we've seen, but now with even higher fidelity; question answering, providing informative answers to queries; code generation, writing code snippets or entire functions. Let's revisit the transformer architecture for LLMs. Many LLMs are decoder-only transformers, meaning they are primarily focused on generating sequences. They have a stack of decoder layers. Each decoder layer uses masked self-attention, ensuring that when predicting the next word, it only attends to preceding words in the sequence, not future ones. Self-attention is critical. For any word in the input-output sequence, self-attention calculates a weight or score for every other word, indicating its importance relative to the current word. This allows the model to dynamically focus on relevant context words. This is done through query, key, and value vectors derived from each word embedding. Multiple self-attention heads are used in parallel, multi-head attention, allowing the model to focus on different types of relationships simultaneously. Perhaps one head focuses on grammatical dependencies, while another focuses on semantic meaning. The outputs of these heads are then concatenated and linearly transformed. After self-attention, the output passes through a feed-forward neural network for further processing. Each layer also incorporates residual connections, allowing information to skip layers, and layer normalization, which are crucial for training very deep networks. The result of this complex, multi-layered transformer architecture, scaled up with immense data and compute, is a model capable of generating astonishingly human-like and contextually relevant text. The final output layer typically uses a softmax function to predict the probability distribution over the vocabulary for the next word. LLMs are the driving force behind the current generative AI revolution, impacting everything from personal assistants to creative writing tools. Next, we'll learn how to effectively communicate with these powerful models through prompt engineering.